This is the third test of the full node benchmark test. So just to refresh, I'll go to that page here. This is the full node benchmark test that I'm running. And let's see, if I switch to unstable branch, here are my notes from the last two tests that I ran, which were also today. In the previous two tests, I ran 300 transactions, and in this test, I'm going to run 3,000, so an order of magnitude larger. I have also, in the last test, I reduced the time between transactions to 200 milliseconds, and the result was that the actual time between transactions came down to about 750 milliseconds per transaction. In this test, not only am I increasing the number of transactions to 3,000, I decreased the time between the artificial delay to 0. So I even went so far as to comment out the sleep function that normally does it. So there's really no delay. This is going to run as fast as it possibly can. And yeah. And so we'll see what happens. In the last two tests, there was no measurable or no significant change in resource consumption. So even at less than 1 second, 1 second per transaction, there still wasn't any appreciable change in the full node. This test is trying to stress the full node. Its typical CPU processing power seems to hang out between 10 and 15%. Its memory footprint is approaching steady state. The other two tests would show up here. I've ran both of them over the last 6 hours. That's probably what these spikes are. I think that was the last test. Yeah, so, I mean, really, they're not even registering. Here is the blockbook indexer. As I mentioned in the previous video, this blip is from when I took the container down and brought it back up. And but you can see the CPU usage. The other two tests are also captured here. This spike in bandwidth right here is from cleaning up the last test, and presumably this flat top here is the last test I ran. Yeah, so hopefully this test will stress this a little bit, because the only way I can get faster throughput from here is if I run multiple wallets in parallel, which I'll get to that. But right now I'm just going to run this one test wallet as fast as it possibly can, and we'll see how the systems react. Right now, so here's the REST API. We'll see the calls come in. Right now there's nothing going on because I don't have anything running. Here is the droplet running REST at idle, not processing anything. It's 2 gigabytes of memory, and it's consuming about 25% of that at idle, and about 4% CPU at idle. And here is the debug log of the full node. We are running version 0.20.10, which is the latest. Here is the droplet running the full node at idle. This is a 2 CPU, 4 gigabyte memory CPU. So at idle, it's using about 20 to 23% of its memory, about 900 megabytes, and it's just sort of hangs out between 10 and 15% CPU usage. Bitcoin D does, just staying in sync with the network and doing its normal thing. Here is the API, or the logs for Blockbook. That's running. Version 0.3.1 is what we're running here. And this is on mainnet. This is all on mainnet. All these tests are on mainnet. So at idle, Blockbook uses about 2% of its CPU power, about 25% of its memory. It's an 8 gigabyte droplet with 4 CPUs. So it consumes about 2 gigabytes at idle right now. And this is running in single-threaded mode, which is easier to understand, but in production it would probably run multi-threaded mode. But then running on your own personal laptop, you'd want to run this indexer in single-threaded mode because it's the most reliable that way, and it's plenty fast for a single user, as these tests are demonstrating. So okay, now that we can see how the state of the systems, let's kick this test off. Bin run node test. Okay. So like in the last video, this code's been modified to show the time between each, calculate the time between each transaction individually, and then it will average them all at the end of the test. Right now it's calculating the 3,000 addresses it's going to spend, and we saw last time there was about 500 milliseconds per transaction naturally. So if it's half a second times 3,000 addresses, that's 1,500 seconds. So this test is going to run for about 25 minutes. So we'll get it kicked off and watch it for about 5 minutes and get a feel for how it's doing and how it's stressing the system. And then I'll probably pause the video and let it run to completion. And then if it truly does run this long, which it will, it should show up very clearly on the 6-hour timeline of the graphs provided by DigitalOcean. This is probably going to take a couple minutes to calculate all the addresses, so I'll pause the video here and then start it once it starts. Okay, here it goes. It's running as fast as it possibly can. Looks like we're averaging a little less than 500 milliseconds. And so that means this test is probably going to take about 20 minutes to run. And so it's just off to the races. It's spending pre-confirmed, all the 3,000 UTXOs have been confirmed in blocks. So this is a stress test of the full node. It's a system-wide test, but the emphasis is on the full node because the indexer is really just reading from its database. So it's not a very stressful thing on the indexer. And like I said, this is the fastest that this system can run right now without concurrency, without running this wallet that's running that we're looking at right now. I would have to run multiple versions of or parallel wallets in order to increase this throughput, which is certainly doable, and I will do in future tests. There we can see the REST API request coming in, and this is the REST API. We can see its CPU has jumped up to probably between 10 and 15%. Its memory usage has not increased at all. Well, maybe, I don't know, 3%, 5%. So the REST API is doing just fine. We could be running multiple threads there if we wanted to optimize. Okay, and then here's the full node. It's still just sitting between 10 and 15% like it does at idle, so there's no significant or measurable impact on the full node. Which means it could probably be transmitting requests and processing transactions much faster than it actually is, which is 500. Let's just call it 500 milliseconds, although it looks like it's a little closer to 400. So it's really not stressed out there. Here is the blockbook indexer. This may actually be the bottleneck here. It's hard to tell because this system is not significantly affected either. And And the CPU is, it's really hard to tell. The memory is sitting at 20%. It's rock steady, really. I'm not even seeing any change. These numbers aren't really changing at all. And the test is running, and the REST API is running, and we can verify that Blockbook is... I mean, this is what I would expect. So the system is being interacted with. And so that's 2 transactions per second that we're generating steadily. And this system using ABC and Blockbook isn't even worried. So, I mean, just based on these numbers, I could probably have 5 or 10 wallets like this running in parallel. And actually, that's what I need to do. I need to build a test doing exactly that. Running this exact same test with 5 to 10 wallets in parallel, so that we can further stress the system and see if we can get these numbers to change at all. Because as far as I can tell, Blockbook and the full node can do 2 transactions per second all day, without and significantly more than that. So I'll pause the video here and let this keep running. And if a significant amount of time will have passed, we'll see a nice representation in these graphs as to how this test is impacting the subcomponents of the system. Okay, the test just ended. It sent 3,000 transactions and didn't have an error at all. And the average speed was 433 milliseconds per transaction. So let's refresh the graphs. Let's see what we got here. Okay, so this is the REST API. So we were achieving a little bit better than 2 transactions per second. And you can see a nice level area there with the bandwidth. And I'm using the public IP addresses between all the components. In production we'd use private, but that doesn't really matter. They're all in the same data center, so the latency should be incredibly small. But so we can see that the test, what time is that? 2:03, 2:14. So yeah, I mean it took significantly less than 20 minutes, but you can see here the memory and the CPU just there's really nothing. There's no there. There's nothing there. There's a slight intake. So what is that average? Is less than 5% there, and then about 10%. So the REST API is not under any significant load. We could probably 10x the number of processes being run on this one lone processor. Here's the full node. This is the one that should really be showing some strain. And again, we have this nice level-ish, or at least noticeable uptick in bandwidth from talking back and forth with the REST API. But we have no significant increase in either memory or CPU usage. So at 2 transactions per second, this full node could care less. It's not even breaking a sweat. And yeah, we're seeing the same thing with Blockbook. We're seeing the memory rise a little bit, but that's to be expected because this is the steady state over here. CPU usage is negligible, and then there's a big spike in bandwidth because it's talking to the REST API. And yeah, so again, 2 transactions per second, not a significant strain at all on this system. And so the next step is to run the same tests in parallel into probably, I mean, I would start with 4 or 5 wallets, running this exact same test. So running five versions of this exact same test in parallel on one system or against one system, and see where that gets us.